Today we will study decision trees, one of the most intuitive machine learning algorithms. Unlike many models that operate as black boxes, decision trees mimic human decision making by asking a sequence of questions. Because of this structure, they are highly interpretable and widely used in engineering applications. They also serve as the foundation for more advanced ensemble models such as random forests and gradient boosting. When you look at the figure, notice how the process starts at the top with a single node and then branches into smaller decisions. A decision tree works much like a flowchart. At each node, the model asks a question about the data. Depending on the answer, the observation follows a different branch. Eventually, it reaches a leaf node, which contains the final prediction. For example, in pavement engineering, the model might first ask whether traffic exceeds a certain threshold, then evaluate pavement age, and finally determine whether the pavement condition is good or poor. This slide illustrates why decision trees are attractive for engineering problems. On the left, we see different sources of engineering data, including pavement condition, materials properties, traffic, and environmental factors. The tree in the center demonstrates how these inputs are transformed into decisions. The key advantage is that the resulting model remains easy to understand. Unlike neural networks, where relationships are often hidden, every decision made by a tree can be traced and interpreted. This transparency is particularly valuable when engineering decisions must be justified to stakeholders. Let's begin by understanding what a decision tree actually is. A decision tree is a supervised machine learning algorithm that makes predictions by asking a sequence of questions. The structure resembles an upside-down tree where we start at the top and move downward through a series of decisions until we reach a final prediction. In the figure, notice how we start the process with a root node and then branches into multiple pathways. Each pathway represents a possible answer to a question. Depending on the answer, the observation follows a different route through the tree. For example, in pavement engineering, a decision tree may first ask whether errors exceed a certain threshold. For example, if error is less than 5%. If the answer is yes, the pavement section follows one branch. If the answer is no, it follows another branch. Additional questions are then asked until a final prediction is reached. What makes decision trees particularly attractive for engineers is that basically every prediction can be traced back to the decision path. Unlike many black box algorithms, we can see exactly how the model arrived at its conclusion. To understand the intuition behind decision trees, think about how engineers make decisions in practice. Suppose you are evaluating whether an asphalt mixture is likely to have high or low moisture susceptibility. You would not immediately make a decision. Instead, you would ask a sequence of questions. For example, what is the air word content? What is the binder content? Is wrap present? What is the aggregate absorption? Each answer helps narrow the possibilities until you arrive at a final conclusion. The figure illustrates the same idea. The model begins with a large group of observations and progressively divides them into smaller and more homogeneous groups. Each split reduces uncertainty and helps the model focus on observation that share similar characteristics. The key idea is that decision trees solve complex prediction problems by breaking them into a series of simple decisions. Now let's examine the anatomy of a decision tree. The figure shows the four major components of a decision tree. At the very top is the root node, which contains the entire dataset. In this example, the first decision asks whether errors are less than 5%. Based on the answer, observations move down different branches. The green and red boxes represent internal nodes, where additional questions are asked. In the green box, the question is about the binder content and whether this is more than 5.5%. In the other internal node, the question is on the VMA value and whether this is more than 15% or not. These questions continue to divide the data into increasingly homogeneous groups. Finally, we arrive at the leaf nodes at the bottom. These are the final outcomes or predictions. For example, the model predicts whether the tensile strength ratio is high, moderate, or low. The key idea is that the tree transforms a complex prediction problems into a sequence of simple decisions. This slide illustrates how a decision tree actually learns from data. The table at the top represents the original dataset. Notice that it contains multiple variables and the corresponding target values. The algorithm evaluates many possible split points. In the center of the slide, you can see examples where different thresholds are tested. The model compares these alternatives and measures how effectively each split separates the data. At the bottom, the algorithm selects the split that provides the greatest improvement in node purity. In this example, the best split occurs at the error content less than 6%. This process is repeated recursively until the tree structure is fully developed. Here we learn one of the most important concepts in decision trees, which is node purity or node impurity. On the left, the impure node contains both red and green observations. It could be observations that belong to two different classes. For example, observations or pavement sections with high TSR values and pavement sections with low TSR values. So because multiple classes are mixed together, there is uncertainty regarding the correct prediction. On the right, there is no uncertainty because every observation belongs to the same class. For example, every observation belongs to the class of high TSR asphalt mixtures. Decision trees continuously search for splits that transform impure nodes into the nodes that come with better purity. The more homogeneous the resulting groups become, the easier it is for the model to make accurate predictions. Entropy is one of the measures used to quantify impurity. This slide shows two extreme cases. On the left, the pure node contains only one class. Since there is no uncertainty, entropy is very low. On the right, the node contains an equal mix of two classes. For example, equal mix of high TSR values and low TSR values, 50% high TSR values and 50% low TSR values. This creates maximum uncertainty and therefore high entropy. Think of entropy as a measure of disorder. High entropy means the observations are mixed and difficult to classify. Low entropy means the observations are organized and easy to classify. The objective of the decision tree is to reduce entropy with every split. Information gain tells us how much a split improves the organization of the data. At the top of the slide, we start with a mixed parent node containing both red and green observations. After splitting, the child nodes become much more homogeneous. The difference between the entropy before the split and the weighted entropy after the split is called information gain. A larger information gain indicates a better split because it reduces uncertainty more effectively. This is one of the primary criteria used when building decision trees. Another popular impurity measure is the Gini index. This slide compares several scenarios. A completely pure node has a Gini value close to 0, while mixed nodes have larger Gini values. The diagrams in the center illustrates how impurity changes as the class distribution becomes more balanced. Most modern implementations, including scikit-learn, use Gini impurity by default because it is computationally efficient while producing results similar to entropy. This slide walks through a numerical example of information gain. At the top, the parent node has a high entropy value because it contains both classes. After the split, the child nodes become significantly more organized, resulting in lower entropy values. The equation at the bottom calculates information gain as the difference between the parent entropy and the weighted entropy or weighted average entropy of the child nodes. Rather than memorizing the formula, focus on the concept. A good split produces more homogeneous groups. This slide provides a side-by-side comparison of entropy and Gini impurity. Notice that both metrics behave similarly. As node purity increases, both entropy and Gini values decrease. The left side illustrates entropy calculations, while the right side shows the corresponding Gini calculations. The important takeaway is that both methods attempt to achieve the same objective, creating nodes that contain observation from a single class whenever possible. Decision trees can naturally handle continuous variables. In the scatter plot on the right, the observations are separated using a threshold value. The vertical dashed line represents a potential split point. Observations on one side of the threshold form one branch, while observations on the other side form another branch. Examples of continuous variables in pavement engineering include air voids, binder content, traffic loading, temperature, pavement age, so on and so forth. The algorithm automatically searches for the threshold that produces the most effective separation. Decision trees also work well with categorical variables. The example on this slide uses aggregate type as a categorical feature. Different categories are grouped and evaluated to determine the most effective split. The scatter plot illustrates how the data can be partitioned according to categorical groupings. This flexibility is one reason decision trees are widely used in engineering datasets that contain both numerical and categorical information. Here we learn about one potential issues in machine learning, and basically it is one of the issues or potential issues in decision trees as well. And it is about the concept of underfitting or overfitting. So basically the left graph shows underfitting. The model is too simple and fails to capture important patterns. The middle graph represents a balanced model that captures the underlying trend without becoming overly complex. The right graph shows overfitting. The model follows every fluctuation in the training data, including noise. Although the overfitted model performs extremely well on training data, it usually performs poorly on unseen data. Pruning is one of the most effective methods for combating overfitting. The left tree contains many branches and is highly complex. Some branches represent only a few observations and may not contribute meaningful information. After pruning, shown on the right, the tree becomes simpler and easier to interpret. Pruning improves generalization by removing unnecessary complexity and focusing on the most important decision rules. Here is a summary of the strengths of decision trees. First, they are easy to understand and visualize. Second, they naturally handle both numerical and categorical variables. Third, they capture nonlinear relationships without requiring complicated mathematical transformations. The example tree shown on the right demonstrates how simple decision rules can generate useful engineering predictions. These characteristics make decision trees one of the most user-friendly machine learning models. Despite their advantages, and similar to other machine learning algorithms, decision trees also have limitations. They are sensitive to noise and outliers. Small changes in the training dataset can sometimes produce a different tree structure. They also tend to overfit if allowed to grow too deep. The figure in the center shows how increasingly complex trees may become unstable and overly specialized to the training data. These limitations motivated the development of ensemble methods such as random forests. And here we learn how to basically implement decision trees in Python. It's a very easy and straightforward coding. So the code on the left imports the model, creates the tree, trains it using the fit function, and generates predictions. On the right, the workflow summarizes the process. First, go ahead and prepare the data. This is basically the first step in any machine learning approach. Split it into training and testing datasets, train the model, evaluate performance, and finally make predictions. Despite the sophisticated theory behind decision trees, implementation requires only a few lines of code. One major advantage of decision trees is their ability to identify important variables. The bar chart ranks features according to their contribution to the model. In this example, Avoids appears to be the most influential predictor, followed by web content and binder content. Feature importance helps engineers understand which variables have the greatest impact on performance and can guide future experimental design and data collection efforts. This final slide summarizes the complete decision tree workflow. It starts with data, data collection and data preparation. The model creates splits that form a tree structure. The tree generates predictions which are then evaluated and interpreted before supporting engineering decisions. The icons at the bottom highlight the major strengths of decision trees. They are interpretable. They handle both categorical and numerical values. They handle nonlinear relationships. They are easy to use and are engineering friendly. And they serve as the foundation for more advanced methods such as random forests and XGBoost. The most important lesson is that decision trees transform complex engineering problems into a series of simple, understandable decisions.